engineering. Today's topic is a fluid flow inside a circular tube. So in this video tutorial, we'll learn about velocity distribution and shear stress inside a pipe under laminar flow conditions using Python. So first let us understand what is flow. When a viscous fluid flows through a circular pipe, it follows Hagen-Poiseuille law for laminar flow. This means that the flow is smooth and follows a parabolic velocity profile. Okay, and the flow is driven by pressure difference across the length of pipe, causing the fluid to move from high to low pressure. Now let us understand what is velocity distribution. As you can see here in graph, the velocity distribution inside the pipe is given with the equation. So here u of r is velocity at radial position r, r is pipe radius, m is dynamic viscosity, l is pipe length, p is pressure drop along the pipe, r is radial distance from the pipe center. The equation shows that the velocity is maximum at the center and zero at the pipe wall, forming a parabolic profile. Now let us understand what is shear stress distribution. So shear stress, it is called as T as well, is the force per unit area exerted by one fluid layer on another due to viscosity. It is given by the equation that you can see. The equation tells us that the pipe center R equals to 0, shear stress is 0. It increases linearly with R toward the wall. At the pipe wall R equals to R, shear stress is maximum. The negative signs means shear stress acts opposite to the velocity gradient resisting fluid motion. So now let us see contour visualization. To better visualize this, let's generate contour plots. This will show how velocity and shear stress are distributed inside the pipe cross section. You will see that the velocity is highest at the center and gradually decreases toward the walls, forming a smooth parabola. Similarly, shear stress is 0 at the center and increases towards the pipe wall. So in summary, we can say that the velocity follows a parabolic profile, being highest at the center. Shear stress increases linearly from the center to the wall. Contour plots gives us the clear visualization of these distributions. So now let us understand the contour code like graph. So now let's go through a step-by-step guide where I'll show you how we can make velocity and shear stress distributions inside a circular pipe. So first of all, we are importing the libraries. Then we are defining the parameters. So here R is the radius of pipe set to 5 centimeters, L is the pipe length set to 1 meter, Mu is the viscosity of a fluid given in Pascal seconds. Then we have delta P is the pressure difference driving the flow through the pipe. Okay, and then we have here Rn line space. So this basically generates the radial positions. So we are creating an array of 100 evenly spaced points from 0 center of pipe to R pipe wall. These points represents the radial positions where we will compute velocity and shear stress. Then we are calculating here. So using the Hagen-Poiseuille equation, we can compute the velocity at each radial position, and you all know the formula that is written over here. Velocity is maximum at the center, r equals to E. Velocity is 0 at the pipe wall, r equals to R. And velocity distribution follows a parabolic shape. Now let us calculate the shear stress distribution. So for that we also have a formula where here is the formula. As you can see, the shear stress is 0 at the center, r equals to 0. It increases linearly as we move toward the pipe wall. The negative signs means shear stress acts in opposite direction to the velocity gradient resisting fluid motion. Okay, then let's begin plotting some graphs. So here is the velocity distribution in circular tube, where x-axis represents the radial position and the y-axis represents the velocity. The parabolic shape confirms that the velocity is maximum at the center and decreases towards the wall. Then we have a plot of a shear stress distribution in circular tube. So here x-axis represents the radial position and y-axis represents the shear stress again. So we observe that linear increase in the shear stress from the center of the wall. Now let us have some contour plots, and for that we need to do some calculations for the mesh grid here. So to create contour plots, we first design 2D grid using the NP mesh grid function. We then convert these Cartesian coordinates to the polar coordinates since the pipe is circular. So that is why we are creating these equations using the same velocity and shear stress equations. We compute the values for each point in 2D grid. Values outside the pipe are set to NaN, which is the null value, to this circular cross section. Okay, and now let's plot it. And as you can see, the contour represents velocity distribution in pipe. The center has maximum velocity shown in the red. The velocity reduces towards the wall as shown in the blue. And this is the plot for shear stress contour in circular pipe. Shear stress increases linearly from the center to the wall. The wall experiences maximum shear stress as indicated by the dark colors here. And this completes our Python-based visualization of velocity distribution and shear stress inside a circular pipe. Feel free to experiment with the different parameters to see how they affect the flow. Thank you.